like I'm on a pilgrimage. Got my Scottish tartan dress, my kilt, my special chapeau. Now, where am I? That's what you'd like to know. Well, who is the most famous physicist who ever lived? Some would say Isaac Newton. I might say Galileo. But I think if you said James Clerk Maxwell, nobody would disagree with you. So that's a hint. A very strong hint. This is where he grew up. This is the park he used to play in. This is where he didn't get into university. And instead, eventually had a petition to go to Cambridge.
Ah, Edinburgh, the city where I first chased light through the mist. At 14, I was already puzzling over the mathematics of curves and colours, scribbling equations. Didn't pass every exam, mind you. Cambridge nearly said no. But curiosity is a stubborn thing. It carried me from these cobbled streets to the laws that would bind electricity and magnetism forever. Funny, isn't it? A boy who once built spinning colour wheels ended up spinning the entire universe.
As my friend Professor Brian Keating always says, A, B, C, always be curious.
Look at this. They're using electric chargers in the place where James Clerk Maxwell grew up. Pretty cool. Right across from his house, there are electric chargers. There's even a Tesla. Tesla charging right by James Clerk Maxwell's house. For the greatest scientist in history, there was the paradigm. Talking about James Clerk Maxwell. Maxwell was born 1831 at 14 India Street in Edinburgh, Scotland. And that is where I am today. Paying homage to the physicist some would say was the greatest of all time, the GOAT. He lived here for many years. He enrolled in advanced education as a youngster, not far from where we are right now, on India Street in Edinburgh. By age 16, he was learning about calculus, teaching himself all about it, and even making original contributions to the subject. He left for Cambridge when he was just 19 years old, June 13th, 1831. Some would say the greatest physicist who ever lived was born. James Clerk Maxwell, right here, 14 India Street. Let's have a look. They called him a natural philosopher. Didn't mean that he was a philosopher. It meant he was a theoretical physicist. So we read from Einstein himself. Many of today's technological advances are due to James Clerk Maxwell, who created the first color photographic image and developed the theory of electromagnetic waves, which made radar and GPS possible. It's commemorated by a statue on George Street, which we'll take a look at. And this is a small museum right at his birthplace. You have to make an appointment to come here, and it is called the International Center of Mathematical Sciences. So with a little luck, we'll be able to go into this great building in not too distant future.
Your eyes are only susceptible to red, green and blue, but you can make any, like RGB, you can make any colour by a combination of reds and greens and blues. You know, and so he took these black and white photographs and the red light and the blue light, and miraculously got to this colour diagram. And so the audience was able to see colour for the first time. This is supposed to turn, you know, you have to spin this very fast. And you get a precession. And the clever thing is adding this coloured top to it. Because when the axis of precession passes through the yellow, the axis of precession goes round. You can imagine the thing precesses round a certain axis. And when the axis of precession passes through the yellow, you only see the yellow. You don't see this blue, or you don't see red, you don't see green. It's amazing.
He never lost track of Edinburgh. This city remained in his heart his whole life. The people. I think it's just spectacular that they preserve the memory of someone who almost nobody knows about. Even the people charging their Teslas across the street here have no idea that the man who came up with a theory of how we could get electromagnetic charge in motion to create electromagnetic fields, lived here. And it's quite spectacular to think this is where he came from. His masterpiece, 1865, Theory of Electrodynamics, a theory of electromagnetism, brought light to the world. There are t-shirts you can get that say the 4 Maxwell equations, the 2 ancillary equations, and they say that's what God said first, and then he said, let there be light. It's quite spectacular to be in the place where it all began, almost 200 years ago. 1865, the world was very different. The United States was just coming out of the fiercest war we had ever had, the Civil War. Europe was still led scientifically primarily from the United Kingdom and England, but that title would soon pass to the United States. But Maxwell's contributions were the inspiration behind many of today's inventions, including those Teslas being charged right across the street from where the great Maxwell was born. Maxwell's equations are sort of the foundation for all of modern physics. They provide the basis of, in fact, for the Yang-Mills equations. It's described quantum chromodynamics. The unification of electricity and magnetism led to almost all of modern society. Now, one thing that's not really appreciated very much is how Maxwell was caught between the classical world and the quantum world. And even a mind as great as his could not comprehend how the waves that he predicted of electromagnetism propagating at an incomprehensible speed, how they could propagate in a vacuum. So his model involved sort of sets of gears and pulleys and all sorts of other things in what we would call the ether. And then just a mere 40 years later to the day almost, Albert Einstein's famous 1905 paper proved beyond a shadow of a doubt that no ether was necessary. But what was necessary was a radical rethinking of time and space. How time and space could both be relative. Relative to what? To the observer's frame of motion. But what was absolute, the only thing that was absolute, is the ratio between time and space, namely speed. And only one speed is absolute. And of course, that's the speed of light, which he knew emerged from his equations. And yet he still had to have this mechanistic formalism for developing electromagnetic waves. Maxwell died young, only age 48. He didn't get to live to see what Einstein would later show as the crowning achievement of his life. We already saw how Einstein revered James Clerk Maxwell. But it was forgivable that Maxwell would think that light needed a medium in which to propagate. After all waves seem to, at least the waves known at that time. So why would light be any different? This is well before the quantum revolution that he was trying to discern how light could possibly propagate at such an unimaginable speed. What was needed to make that happen? Air, water, sound, they all needed mediums to be supported in. Light was no different. So he constructed a theory with gears and vortices that would transmit mechanistically, almost bridging the classical and quantum worlds. Of course, we know there's no gears and pulleys within it. And as Michelson and Morley would show, just a mere 30 years after Maxwell's equations were produced, that there is no absolute frame of reference that an ether would produce. Eventually, Einstein showed that photons themselves are quantum objects. And this was a revolution and a revelation. Stay tuned for more facts about the great James Clerk Maxwell. I'd like to think that Maxwell would like this vlog, using as it does color photography, which he invented in 1861, even before he came up with his 4 laws of electromagnetism. He came up with the color photograph. His idea was simple but radical. All colors can be made by mixing together red, green, and blue. He knew that. What Maxwell did is use photographic plates, but those could only see monochrome, just intensity, not color. So what he did was take a separate filter, a red filter, a green filter, and a blue filter, and then he would expose the image onto the photographic monochrome plate. After doing so, he then projected and combined those three colors together using a light source for each, and then they all were projected onto the same screen. The result was a full color photograph. And this actually links him to Isaac Newton, who knew about the laws of color combination and addition and subtraction, connecting the two great physicists of their respective generations on this lone island. Maxwell showed that color wasn't just art, it was a science that could be understood. And later, just 4 years later, he would come up with an idea that would link together colors of all wavelengths, including colors that can't be seen by the human eye. Maxwell was a true polymath. He even wrote poetry. He came up with a theory of electromagnetism. He invented color photography. He tried to do his hand at experimental physics. He helped create the standard unit of electric resistance, later called the ohm. He conducted early studies on Saturn's rings, and he surmised that Saturn's rings must be comprised of tiny particles due to their scattering of light and that behavior. He later became an academic trailblazer, becoming a professor at Cambridge of experimental physics, founding the Cavendish Laboratory at Cambridge, which is legendary. Cavendish became the home of the discovery of DNA, of the neutron, of the electron, and the neutron. At 14 years old, he was a prodigy already. Came up with a paper that was published in the Royal Society Transactions on mathematics. He died of stomach cancer at the young age of only 48 years old. His face is engraved on the Scottish £1 banknote. Maxwell didn't just speculate about light, he did experiments on it. He was one of the first to understand what polarization was and why it was so important. He showed that polarization of light isn't just an accident, it's a natural consequence of the existence of electromagnetic fields, which Faraday had coined, but Maxwell had proven the existence thereof. And I like to think about explaining to him how the Simons Observatory is seeking out cosmic polarization, trying to understand it. Not in the visible light spectrum, as he explored, but in the microwave part of the spectrum, which he certainly knew about. Now, the most exotic thing we could possibly detect is called cosmic birefringence. Bi meaning two, refringence meaning refractions. That would be the case if light propagates at two different velocities, depending on whether it is polarized horizontally or vertically, or if you like, circularly left or circularly right. Now, claims of this detection have been made using Planck satellite data, but we in the Simons Observatory trying to understand if we can do a more precise and accurate estimation of what the polarization of the CMB looks like and how exotic new physics could manifest itself. This would break so-called Lorentz invariance, which is an underpinning, ironically, of the special theory of relativity that Einstein used to demolish Maxwell's understanding of the ether. Even though Maxwell had predicted with uncanny accuracy the speed of light and the propagation of radio waves and all electromagnetic radiation at the speed governed by his famous 4 equations, he died more than a decade before he could see experimental verification of their reality. In the 1880s, a decade after Maxwell died, it was discovered that light and all forms of electromagnetic waves refract, reflect, and propagate at the same speed, no matter what the wavelength is. Here's a train coming by, powered by Maxwell's electricity. Without Maxwell, there'd be no color photography, no Wi-Fi, no electric power, and no light, at least the kind that we enjoy. Stay tuned for more videos about Maxwell and electromagnetism.